Oh, what happened? No, okay. Okay, welcome back. Do you have any questions before I start? Can you hear me well?
Yes, we are hearing you, Doctor.
Yes, doctor.
Okay, good. So last time, let me just remind you very quickly what we did last time. Last time we introduced the general form of a system of linear equations, right? We said that a system is made of m equations. This number m can be any, of course, starting from 1. And it contains n unknowns, which here we labeled x1, x2, and xn. Okay, and the system looks like this one here, and it has the coefficients, which are these a11, a12, a1n. These are the coefficients of the first equation. Similarly for the second equation, and so on. And it has the right-hand sides, which are just numbers b1, b2, and bm. So you see that every system is made of some equations, and every equation is equivalent to an expression, a linear expression in the variables, equal to some constant b1, which we call the right-hand side. Okay. So these numbers are usually called scalars, b1 and b2, right, and so on. And so are these a11. These are called usually the coefficients of the system, okay? But these are, again, scalars. They are just real numbers, okay? Yeah, of course, we are going to confine ourselves to real systems of linear equations, although in general, you may discuss complex systems where the numbers are complex numbers, if you are familiar with them. But in this course, I will confine the discussion to the real case, where all the coefficients are real numbers. Okay, and in that case, the solutions are going to be just real solutions. So we will be seeking only real solutions. Okay, so I'm not interested in any complex solution. In fact, if you make the assumption that the coefficients are real and the right-hand side are real, then the solutions automatically will be real as well, okay? So we'll focus only on real numbers. Okay, there's a special case when the right-hand side vanishes completely. So when all these B1, B2, and so on, BM, all of them are zero, in that case, we say that the system is a homogeneous system. Okay? So this is a very special case. And it simply means that the right-hand side, which means the coefficients which do not contain the variables. So you see there are no x in these coefficients. Okay, all these are just zeros. In that case, we say that the system is a homogeneous system. Now, a homogeneous system, it turns out, it always has at least one solution. So if you take a system like this one here, like the one here, okay, then this one at least has one solution. Of course, it may have more than one solution, but we are sure that there is at least one solution, and this solution is just the zero solution. As we say, this is the case when x1, x2, and all of the x's are just. And you can easily see that this is going to be a solution, because if you replace here x1 by 0, x2 by 0, and xn by 0, then the left-hand side will be 0, and it will automatically be equal to the right-hand side. And of course, this is going to be true for the second equation and for all the equations. Okay, so we say that a homogeneous system admits at least one solution, right? Namely, the solution where all the unknowns are equal to 0. This is what we refer to as the zero solution. Okay, but in general, you may have more than that. You may have another solution. In fact, infinitely many solutions other than this zero solution. Okay, but just keep in mind that whenever the system is homogeneous, meaning that the right-hand sides vanish identically, all of them are 0. Then the system admits at least one solution, which is a zero solution. And because of this, the system is going to be consistent. Remember, we introduced this terminology last time. We said that the system is said to be consistent if it admits at least one solution, and otherwise it is said to be inconsistent when there are no solutions. So a homogeneous system is always consistent because it has at least one solution, namely the 0-0 solution. Let me give you an example before I proceed to the next thing here to do. Let's take a special example of a homogeneous system. Let's say we take this system 2x minus, let's say, y equals 0. Okay, and I will keep it simple. Two equations into unknowns. Let's say x plus y equals 0. Okay. Now, is this a homogeneous system? We ask. Now, how can you tell? You see, the system is going to be homogeneous only in case when the coefficients, right, as we call them usually the free terms, which do not involve the variables x and y, when these numbers are 0. And we see here that they are, right? So the right-hand side here is 0. So this equation is homogeneous, and so is this equation. This equation is homogeneous too. Now, then, okay, I claim that this system is consistent, meaning that there is at least one solution, right? There's at least one solution, okay? And what can this solution be? Now, we can easily see that the solution is going to be the 0-0 solution, right? Because if you remember our interpretation of these equations, this is a line, and so is this. And the two lines here are passing through the origin, right? The 0-0 point. So x equal to 0 and y equal to 0, right? This is a solution, okay? Because you can just check them. If you replace x by 0 and y by 0, you will get 0 equals 0 in the first equation, and also in the second equation, you will get 0 equals 0. So yeah, this is a solution, right? And we see that this system, which is a homogeneous system, has this solution. In fact, this is the only solution. This is the unique solution, so there are no other solutions in this case, but it could be otherwise, okay? So here's an example of a homogeneous system which admits a unique solution, namely the 0-0 solution. Okay? Do you have any questions about homogeneous systems? No questions, I presume, right? You have no questions about homogeneous systems. Okay. And now we come now to, in fact, we have started this last time, I remember, right? So what do we do now to solve a system of equations? So we have considered the interpretation of this system in terms of lines in the plane, right? But when it comes to solving the system, we want an efficient, if you like, procedure or tool, right, that allows us to get the solution, or to get as fast as possible to the solution of a given system, or at least to be able to see that there are multiple solutions or there are no solutions, right, and so on and so forth. In other words, we want, if you like, to devise a tool, right, or a way in which a system can be easily solved. Okay? And the tool is familiar to you. And all we have to do is just manipulate this system a little bit. Okay, so what do I mean by manipulating the system? Or if you like, you can think of it as transforming the system, changing it a little bit. Okay, so what can you do with the system? First of all, you can, if you like, you can switch the order of any two equations in the system. You can make the second equation the first and the first equation the second. So let's focus now on this system here, for example, right? I can simply make the first equation the second equation and the second equation the first equation. In doing so, the solution will not change, right? Because I'm still solving the same two equations, but now I have simply changed their order, which is completely immaterial when it comes to the solution, right? The solution is still the same solution. Okay, this is the first thing. The second thing, I can multiply any of these equations by a non-zero number. For example, I can multiply the first equation, this one here, okay, by, let's say, 2. 2x plus 2y equals to 6. Okay, now the question is, have I changed the system? Is it a new system? So now if I, let me just copy here, so it's x plus y 3.
It's not a new equation because it is the same value.
Yeah. Okay. So now we'll come to it. So who spoke?
Bakr.
Maybe you can hear me well. Yeah, I see. It's the connection is poor. Yeah. Okay. So I need to warn you, my connection is poor apparently, and it may disconnect any time. So stay please in the meeting and wait for me to reconnect if I got disconnected. Okay. So now this is a system, and now I'm going to change it into a slightly different system. All I'm going to do is multiply, let's say, the first equation by 2. That's it. Okay. So I will make it now 2x, right, plus 2y equals to 3. And the second equation, I will keep it as is, y minus x equals 5. And now, instead of solving this system, let me now try to solve this system. My question is, will the solution of this one, will the solution of this system be identical to the solution of the other system? I mean, if I take this system, no, not this. I want a rectangle. Just a minute, please. So this is a rectangle here. Let me pick the right color. Let's make it red. Okay, so I'm asking, apparently not. Okay, no. Yeah, so will this system, okay, let me now just circle it. Will this system admit the same solution as this system? This is the question. And the answer, of course, is yes.
But the 3 will be a 6, not a 3.
Did I? Yeah. Okay. Yeah, it's my mistake. Yeah. Sorry, I forgot to multiply here by 2. Right. Yeah. Thank you. Yeah, this is 6. Right. Absolutely right. So my question is, if I change this system by just multiplying the top equation by 2, and of course, when you multiply an equation, you have to multiply not only the left-hand side, but the right-hand side as well. So you have to multiply the equation throughout, right? All the equation. And if you change it now into this, now, will the solution of this system be the same as this one, and vice versa? Will the solution of this system be a solution of this?
Yes.
And the answer is obviously yes, because if you assume you had a solution here, let's say you had some values of x and y, which will make the first equation true, right? Then multiplying through by 2, right, will still make it true. I mean, because if we had, let's say here 1 and 2, let's say 1 plus 2 is 3, right? Then if you multiply through by 2, it will be 2 plus 4 equals to 6. It's still correct. It's still correct, right? So if you find any solution to this system, it's going to be automatically hello, can you hear me now?
Yes,
doctor.
Okay. So I was saying, I'm not sure that you heard me. So I was saying that if I find a solution to any of these systems, it's going to be automatically a solution to the other system as well, right? And this means that multiplying an equation by any number, non-zero number, okay, will not change the system basically, in the sense that the solution will stay the same, will not change. Okay? So this is the second operation that I can do. And the last operation that I can do is to replace any of the equations, right, by an equation multiplied by a number and added to the second equation. So this means what? This means that, for example, if I go to this system here, right, then I can, for example, do the following. I can keep the first equation as is, the same equation. Okay. And I can change the second equation in the following way. What I'm going to do is, let's say, multiply the top equation by 2 and add it to the second equation. Okay? So if I multiply it by 2 and and add it to the second equation. Now I need to remind you perhaps here what it means to multiply by 2 and add. It means you multiply the left-hand side by 2 and you add it to the left-hand side. You multiply the right-hand side by 2 and you add it to the right-hand side. Then what's going to become of the equations? Let's see. If I multiply the top equation by 2, I will get 2x plus 2y. If I add it to the bottom equation, I will get 2y plus y, 3y. 2x minus x is x, right? So I will get x plus 3y. Okay? And of course, I do the same to the right-hand side. So multiply the right-hand side of the top equation by 2, this will give me 6, and add it to the bottom equation, which will give me 11, right? So this is going to be now my new system. This is going to be now my new system. And now the question is again the same. If I have a solution to this system, is it going to be a solution to this one? Yes, of course it's going to be a solution to this one, because what I have done here is, you see, I have taken the x and the y here, whatever the solution is here, right? I multiplied it by 2, so it's still true. This top equation is true, and I simply added it to the second equation. And this means that if the left-hand side of the first equation is equal to the right-hand side, and the left-hand side of the second equation is equal to the right-hand side, then the sum of the two equations, the left-hand sides, is going to be equal to the sum of the right-hand side. This is quite obvious, right? So this means, yes, if I have a solution of this system, it's going to be also a solution of this one. And vice versa. If I have a solution of this one, right, then I can simply multiply this equation by -2, right, and add it to this one to get back to my second equation, to this equation. Okay? And this will still be true. So in short, what I'm trying to tell you is something which is very familiar to you, and you have done it many times in your life. Whenever you are trying to solve a system of equations, right, what you can do is one of three things, or many of these, if you like. You can simply switch the order. You can multiply any equation by any non-zero number, and you can multiply an equation and add it to the second equation and replace it, or another equation and replace it, right? So these are called the elementary operations that we do on any system of equations to solve it, okay? So these are the operations. There are three. Switching order or interchanging order, multiplying an equation by a non-zero number, replacing an equation by itself, added to another equation, any other equation you want, okay? Let me illustrate this. Let's try to illustrate this on okay? So we want to show that this system, the system of equations here, has the same solution as this one. Okay. By the way, if two systems have the same solution, then we say that they are equivalent. The two systems are equivalent, meaning we can go from one to the other using these elementary operations, switching order, adding equations, multiplying equations, and so on. Okay. So how can we show this? How can we show that this system is equivalent to this one? And if you look carefully here, what has been done is the x has been eliminated, right? You see the x in the second equation has gone now. There is no x, right? And as you remember, the way to eliminate the x here is to multiply the equation by -2, the top equation by -2, right? And add it to the second equation. Okay? In this way, the -2x will cancel the 2x, and you will be left only with y, which will be essentially this. And this is it. It's being done here. You see, so this is the bottom equation. It's here. This is the left-hand side, the expression, right? And then we multiplied the top equation by -2 here. We added them, and we did the same to the right-hand side. And this is what we get. We get this. Okay? And so now I replaced the second equation. The second equation has been replaced by this one, which is the top equation multiplied by -2 and added to the second equation. Right? And these two systems are equivalent because they admit the same set of solutions. They have the same solution. Okay? Now, this is called elimination. So this procedure here is called elimination of one of the unknowns. We have eliminated the x, and now we can easily solve now for y, right? This equation can be easily solved for y. And once you have y, now you can find your x by what is called back substitution. You can substitute back now in one of these equations, for example, here. If you substitute the y here, you will get your x. Okay, so let me now try to illustrate this. Before I go over the general procedure, let me try to illustrate this on a simple example. Let's try to solve this system here. So suppose we want to solve this system, or maybe, yeah, this system is very easy. Let's try to take another one. Let's say this one, which is the same, right? Okay, let me take this. This one is homogeneous. Okay, let me just rewrite it. So let's say we have 2x minus y equals 2, let's say, right? And x plus y equals 1. Okay, I want to solve this system. Okay, so what can we do? First of all, of course, I can do many things here, but one thing is to replace the first equation by the second equation multiplied by -2 and added to the first equation. Okay, so the second equation is going to stay the same. The second equation will stay the same. I'm not going to change it. The second equation will stay x plus y equal 1. Now, the first equation, what I'm going to do is multiply this equation by -2 and add it to the first equation. So it will be -2, okay, times x plus y plus the left-hand side here. Sorry, plus the left-hand side here. Plus 2x minus y. And of course, I have to do exactly the same in the right-hand side. So I multiplied this one by -2, and I added it to 2, right? So this will give me just 0 here, right? Do you agree? -2 times 1 plus 2. This will give me 0. Okay, let's now try to simplify it. So now, if we want to simplify it now, what do we get? This is an x here. It looks like a k, but this is an x. So the 2x will go away, right? Because it's cancelled by the -2x, and you will get -3y equals 0, okay? And x plus y equals 1, of course. And of course, from here now, it follows that y is equal to 0, because, I mean, how can you get 0? There is no way you can get 0 on the right-hand side except when y is 0. And of course, if you now substitute this y in here, all right, you will get the value of x. So now this together now gives you what? It gives you, this is a plus here, right? X is equal to 1. X is equal to 1. So what's the solution? The solution set then is this. In the solution set, there's only one solution, x equal to 1, right? And y equals to 0. That's it. So I have a set of one solution. So it is a unique solution, right? And the system, of course, is consistent. Do you have any questions?
No, doctor.
Okay. Now, let's move on now to something a little bit maybe new. So it's not, I'm not sure whether it is completely new, but I think, yes, it is. Okay. So this can be done, of course, with any system of equations, not necessarily 2 equations and 2 unknowns. The book is illustrating it for the case of 2 equations and 2 unknowns. Okay. But essentially, it's telling you that this is general and you can apply it to any case. Okay. So I'm not going to go over the proof because it doesn't involve anything new. It's just the well-known thing that you are familiar with from the school. Okay. I'm going to skip also this example. I would leave it to you. If you need, you just read through here to solve this. But essentially, you'll have to do exactly these operations. You have to follow the operations to find the solution. Okay. So unless you have any questions about this one, I'm just going to skip it because it's exactly what you used to do in school. There's nothing new in it. Okay.
Doctor?
Okay. Yes.
This is what I have been asking about the last time. When we had 3 unknowns, we should have 3 equations to solve the system?
Not necessarily. I mean, you may have only 2 equations, or may have even 4 equations, but sometimes the system may be inconsistent, meaning that there is no solution. And sometimes you may have infinitely many solutions. So instead of one solution, you will have infinitely many solutions. In general, if you have an equal number of equations as the unknowns, so let's say 3 equations and 3 unknowns, or 2 equations and 2 unknowns, or 4 equations and 4, then what you should expect is a unique solution, one solution, right? If you have more equations than unknowns, let's say 3 equations but only 2 unknowns, right? Then you should expect inconsistency, no solution in general, right? But if you have now more unknowns than equations, or less equations than unknowns, let's say 2 equations but 3 unknowns, right? Then you should expect infinitely many solutions. Okay? But so there is no rule that says that the number of equations has to be equal to the number. It may be the case, and it may be not. Let me show you an example. So instead of saying this in Word, let me show you an example. So take this system. Let's take a system of 2 equations and 3 unknowns. Okay. So here's a system x, say 2, okay, and x minus z equals 1. Okay, do you agree? It's a system of 2 equations, right? How many unknowns are there? There are 3 unknowns, right? X, y, and z. Okay, and if you remember what we said about it, each one of these equations is a plane, right? So now in the space, now 2 planes, and you know that these 2 planes are going to intersect somewhere, right? In a line, going to be a line. So the set of solutions here is infinite solutions, because 2 planes intersect in a point, right? Because you have a line, which is the intersection, then the line contains many points, infinitely many points, and there should be infinitely many solutions. Okay. So now, how do you find these solutions? How do you find these solutions? The way to find them is to here, in this case, we speak of the free variables and the basic variables. Because you have now only 2 equations, but 3 unknowns, then one of the unknowns is going to be free. In what sense? In the sense that you can give it any value you want. You can give that unknown any value you want, and then from that value, you can find the other 2. For example, if I take x to be the free value, and usually this is denoted this way, let's say x is equal to t, okay, where t belongs to the real numbers, any real number, okay? And then you plug it in here, you replace x by t, but now t, now you treat it as a number, just a number that you know, right? Then you will get t plus y equals 2, okay? And t minus z equals 1. And now you solve these equations as if you knew t, as if you know this t. So the y is going to be equal to t minus 2, right? And the z is going to be equal to, okay, let me write this way, t plus 1. Okay, so now what is the solution? The solution is the set of all triples. What are they? X equal t, y equals 2 minus t, sorry, I missed the equality sign here, and z is equal to 1 plus t. Okay, all these triples where t belongs to the real numbers. For example, let's take an example. Let's say t could be, let's take t to be 0. If t is 0, then what's the solution? The solution is x equals 0, okay? Y equals 2, right, from here, y equals 2, and z is equal to 1. Okay, and you can try it. If x is equal to 0, then y will be equal to 2, right? Did I miss something here?
Z equal t minus 1, t minus 1.
I think here it should be minus. This one should be minus here. Should be minus 1 here. So I think here minus 1 plus t. Yeah. So this will be minus 1 then. If t is 0, then it's going to be minus 1, right? If t is 0, which means x is 0, then z is equal to minus 1, and this will give me a solution. Now, but I mean, t need not be 0. T can be any number. You see, t is just a real number. I can take it, for example, to be 1, let's say. In that case, what do I get for x? X will be equal to 1, right? What about y? Y, by this formula, you see, I'm just reading from here. Y is equal to 2 minus 1, so it's just 1, right? And z, what about z? Z is going to be, in that case, 0, right? Because minus 1 plus 1, it's 0. And let's check now, is this a solution? Of course it is a solution, because 1 plus 1 is 2, right? And 1 minus 0 is 1, right? Absolutely right. So this is a solution, this is a solution. And now, no matter what value of t you pick, any value you want, minus 1, minus 7, minus 11.4, whatever you want, okay, it's going to give you a solution, right? So how many solutions are there? Infinitely many, right? Infinitely many, and they depend on this value of t, which you can give any value you want. Okay, so this is the answer to your question. The answer to your question is the number of equations need not be equal to the number of unknowns. It can be less, it can be more. In this case, it was less, right? If it is less, then you should expect infinitely many solutions. If it is more, you should expect no solution. Okay? Let me now switch back to the new thing that I want now to tell you about, okay? Which will make your life much easier now when it comes to solving equations of or systems of linear equations like this, okay? So what we are going to do is replace a system like this one here. We're going to replace it by a new object, which we call the matrix, okay? And the matrix is just, you see, this array of numbers, this table of numbers, okay? What are these numbers? These are just the coefficients of x, y, and z in every equation in here, you see. How can I, just give me a minute, let me run this annotation tool so I can tell you what I have in mind. Here I can show you at least. Just a minute. Okay, so these coefficients here, this matrix here, okay, is these are the coefficients of these equations. So this is the 1, which is this one here, you see, the 3, which is this 3 here, the 6 here, and so on. The second equation has a 2 for the x, so you see here the first entry in this row is the 2, and then the 7, and then the 14, and so on. So what we are doing is we are taking the coefficients of all the equations and we are arranging them in a table, right, like this. And this table is called the coefficient matrix, okay? This is called the coefficient matrix. Okay, and now the right-hand side, all these numbers, okay, we put them in a separate column. This column here, you see 25, 58, and 19, okay? And together, the right-hand sides and the coefficient matrix, they give you a new matrix, which is called the augmented matrix, okay? The augmented means it is expanded, and this means it is the coefficient and the right-hand side. Okay, so the augmented matrix of any system is just its coefficients, coefficients of the unknowns, and the right-hand side. Okay, let me show you on this example. So what would be the augmented matrix of this system here, of this system? Okay, what would be the augmented matrix? Okay, so look how I do it. I take the coefficients of and the y.
1 minus.
Yeah, so in the coefficient matrix, I have 1, 1, and 0. Remember that here there are 3 unknowns, right? X, y, and z. But here, z is not appearing in the first equation because its coefficient is just 0, right? In the second equation, I have 1, but no y. There is no y, right? So it's 0, and minus 1 for the z, okay? Now, this is a coefficient matrix, and now I put this line here, okay? And then I write the right-hand sides, okay? So this is 2, 1, okay? And this is called the augmented matrix, augmented, okay? So this is the coefficient matrix. Let me try to circle it. This is the coefficient matrix, okay? And all this is called the augmented matrix because we have augmented to it, or we have adjoined to it, or added to it the right-hand side. So this is called the augmented matrix. Okay? Now, what are we going to do now? So now look, if I know the system, I can write its augmented matrix, and vice versa. If I know the augmented matrix, I can write the system. Okay, for example, from here, I can read the first row. By the way, the matrix is made of rows. There are rows and there are columns, right? These are the columns. Okay. So here, in our case here, this matrix has 2 rows, right? There are 2 rows and there are 4 columns. Okay. So the first row gives me the first equation. The second row gives me the second equation. So now, what does the first row tell me? It tells me that there is an x in the left-hand side. There is also a y plus y, right? There is no z, okay? And the right-hand side, which is the number that comes after the line, is 2. So I write x plus y, right? Plus 0z, because this is a coefficient of z, which is 0, right? 0z is equal to 2. This is the first equation. And second equation, it says x plus 0y, right? Plus minus 1z.
Minus z equal 1.
Yeah. And now we can simplify it. We can simplify this, right? And this would give me x plus y equals 2. And the second equation would give me x minus z equals 1, which is exactly my system, right? Which is my initial system, this system. So what I'm trying to tell you here is the following, that if you are given a system of equations, you can always represent it using the augmented matrix, and vice versa. Given the augmented matrix, you can always use it to reconstruct, if you like, the system of equations. Okay, so in other words, every system of equations is equivalent to an augmented matrix. The number of rows in the augmented matrix is equal to the number of equations, right? And the number of columns is equal to the number of unknowns plus the right-hand side. So, for example, here I can see 4 columns, right? This is because I have 3 unknowns, x, y, z, and I have the right-hand side. Okay. And now, instead of looking at the system, we are going now to look at this matrix and see what can I do with this matrix, okay, in order to solve the initial system. So what can I do with this matrix? You see, of course, my goal is to solve this. I want to solve this one. I want to solve this system, right? But now, instead of dealing with the system itself, I'm going to replace it by the augmented matrix and see what can I do with this augmented matrix to make it simpler, so as I will be able to solve the system eventually. Okay, so this is my task. My task is now to use the augmented matrix to solve the system. Okay, do you have any questions about the augmented matrix?
No, doctor.
No questions. Okay, good. Then let me then tell you what you can do. So what we can do to the augmented matrix in order to solve now a system of equations. It's exactly what we did with the system. So let's remember, what could you do to the system? First of all, we could switch the equations, right? We could switch any 2 equations in the system. Okay. We could also multiply one row by a non-zero number, right? And also we could multiply a row and add it to another one, right? These are the operations which we call the elementary operations. Okay, now we can do the same to the augmented matrix. You remember that every row in the augmented matrix is an equation, right? So if I can switch the equations, this means that I can switch the rows. So any augmented matrix, you can switch 2 rows in the augmented matrix. This is the first operation. Second operation, you can always multiply any row, okay, by any number you want, non-zero number. For example, this row here, I can multiply it by a number, let's say by half. So it will become 1, and then 3.5, this will be 7, and this will be whatever it is, right? 28 or 29, sorry, 29, right? So you can multiply any row you want by any number you want, okay? And finally, you can multiply a row, right, and add it to another row. For example, you could multiply the second row by a number and add it to the first row. Or multiply the second second row and add it to the third one, or the first row and add it to the third one. Okay. So these are the elementary operations. These are the elementary operations that you can perform on any augmented matrix. Okay, you can simply, again, switch any two rows, multiply a row by a non-zero number, and replace any row by a multiple of another number added to it. Okay, and let me show you now how we can use these operations in order to simplify our matrix. Okay, now what do you mean by simplifying our matrix? I will try to demonstrate this to you here. Okay. So look what I'm going to do. I'm going to do the following. I'm going to, so consider this matrix. Let me rewrite it down here, or maybe, yeah, let me rewrite it down here so it will be easy to rewrite. So this matrix is 1, 1, 1, 0. I'm writing it column by column, 0, minus 1, and then the right-hand side, which is 2, 1. Okay. So I want now to simplify this matrix. In what sense? In the sense that I would like to get as many zeros as possible in any one row. So here, for example, in this row, right, I would like to make, let's say, one of these numbers, which is not 0, the 1 and the minus 1, I would like to make them 0. Okay? And the way to do it, if you look carefully here at it, what can I do with it? I can, if I want to make, let's say, this one 0 here, okay? If I want to make it 0, what can I do? I can multiply the top row by minus 1, right? And add it to the first row. Okay, so this is what I'm going to indicate. Look how. I would say multiply the top row, I will call it row 1, by minus 1. So R1 stands for row 1. Multiply row 1 by minus 1 and add it to row 2. Okay, and the result should be placed where? It should be placed in row 2. That's how I write it. Okay, so let me read it to you. What this means? This means take row 1, multiply it by the number minus 1, add the result to row 2, and replace row 2 by whatever you get. So replace all this in row 2. Okay, so let's see what we get if we do this. Okay, so the first row will not change because I didn't do anything to the first row. The first row will stay as is. But now the second row, let's see. What's going to happen now to the second row? The second row now, this will become now here, let's see, what do we get here? We get 0, right? Because when you multiply by minus 1, this will become minus 1, right? And this will become, when you add it to 1, it will give you 0. Now this will become minus 1 as well. When you add it to 0, it will give you minus 1, right? And finally, when you do this one here, right? You multiplied here minus 1 by 0, so nothing changed here, and this would be minus 1. And finally, we get here now minus 2, right? I multiplied it by 2. I multiplied by minus 1. It's minus 2, and you add it to 1, so you get minus 1. So you get minus 1. Okay. Now I can also multiply the second row by minus 1. Let me do this. Multiply the second row by minus 1, just to get rid of this minus here. You see, I have minus everywhere here, so I can just get rid of it. And let's see what I get. I get 1, 1, 0, right? And then here I have 2. Nothing changed in the first row. In the second row now, it will become 0, 1, 1, and 1, right? Okay, now, so now you see my system, now, so we started with this system, remember, we started with this one, this system, and this was its augmented matrix. Now we have transformed the augmented matrix into this new form. Now, what system do we get from it? What system do we get from it, from this augmented matrix? Yeah, let's try now to rewrite the system. Again, we easily can do this.
Plus y equal to
right,
and
x plus
y
equals to
plus z.
Right. And the second one, you see the x is now 0. There is no coefficient for x, it's 0. And we have now here y plus z equals 1. Yeah, y plus z equals 1. Yeah. Now you may ask, okay, is this any good to me? Maybe not. It's not a lot, okay? Because your system is a very special kind of system now. So maybe we haven't achieved, I mean, a lot of reduction here. The number of unknowns is still the same. It's still 3. We are just dealing with the same number of unknowns. And if you look carefully at this system, you will not be able to eliminate any of the unknowns. I mean, of course, you'll be able to eliminate, let's say, y, but you will get x instead in the second equation, as we had here, let's say. If you eliminate x, you will get y instead, right? So the number of unknowns in any one equation is going to stay 2, right? Now, of course, you may play around with it here. Okay, this is a mistake. I wrote z here. It should be 2 here. This is a mistake. Of course, this is 2 here. Okay, but you see now, the point is, instead of dealing with the system of equations, now we can deal with the augmented matrix. And we can do all the transformations on the augmented matrix, and then when we are done, when we get a simple enough augmented matrix, we can now revert back to the system, and hopefully we'll be able to solve it. Okay, let me see if time permits to show you an example. So let me just take you, I will walk you through this example in the book. Okay, so this is the example in the book. This is the system that we started with. Okay, so this is this system here. And the augmented matrix is 1, 3, 6, 2, 7, 14, 0, 2, 5, and the right-hand side. Okay, so this is it. It is this matrix here. Okay, and now let's try now to make it simpler. I mean, make this matrix as simple as we can. Now, what do we mean, again, to remind you, what we mean by simple as we can? It means try to get as many zeros as you can in the coefficient matrix, in here, in the coefficient matrix. Okay. Okay, so let's try to make this number here 0. It is 2, 0. How can I do this? How can I make this number here 0? All I have to do is multiply the first equation by -2, maybe, and add it to this one. Do you agree? If I multiply the first equation by -2 and add it, or the first row, if you like, by -2 and add it, this will give me 0 here. And what about this 7? It's going to be a 1, right? Because -2 times 3 is -6, plus 7 will give you the 1, and here it is, you see? And then -6 times 2, it's 12, plus 14 will give you 2, you see, it is here. And then -2 times 25, it's -50, plus 58, it's 8, right? So now the second row now has been really simplified, you see? From 2, 7, 14, 58, now we got 0, 1, 2, and 8. Much simpler numbers. Okay, now what next can I do? Let me try to make this now a 0. What do you think? How can I make this one 0?
Multiply row 2 by -2 and add to it.
Absolutely right. Multiply the second row by -2 and add it to the third row. Okay, and let's see, what do we get? If we multiply by -2, then of course, notice here that this 0, right? If you multiply it by -2, it will remain a 0. So when you add, this 0 will remain 0. And this is very good, because if this 0 changed into something else, right, you would have spoiled it. Yeah, so I want it to stay as 0, this 0 here. Okay, and then, so if I multiply by -2 and add it, get 0, right? If I multiply this by -2 and add it, I will get -4 plus 5. This will give me 1, right? And finally, if I multiply this by -2, -16, and add it here, I will get 3, right? So this is what we get, you see? Notice that the first row did not change, the second row did not change either. The only change happened in the last row. And now it became much simpler. Yeah.
The point here is to continue multiplying until we get only one unknown.
Yeah, absolutely right. Absolutely right. So here, sometimes you may get all of these zeros. Now I will come back to this, but in this case here, we got only, you see here, 2 zeros and only 1 non-zero entry. This one here, you see. And now I can now rewrite this augmented matrix into a system of equations. Okay, so what would it read? Let's see. This is the coefficient of x. So it reads x plus 3y plus 6z equals 25, right? The second equation, there is no x in it because the coefficient here is 0. Y plus 2z, right, equals to 8, Okay, and the last equation, you see the last row now, it's very simple. There is no x and there is no y in it, right? Yeah, and z only. Z equal 3. Okay, now z equal 3, I know it, I replace it up here, and I find y, right? Because if z is equal to 3, then y will be equal to 2. And now if you have z and y, you can easily find the x from the top equation. So you see now, this now matrix is now giving me a very simple system, which I can easily solve, right? And by back substitution, I can get all my unknowns. Okay, I will stop here for now. I will assign a little homework for the next time, and the homework will involve a little bit of these augmented matrices and some systems for you to practice. Okay. Do you have any questions before we dismiss? Yes.
Can you please send us a Jamboard link?
Say it again.
Can you please send us the Jamboard link?
Oh yeah, yes, absolutely, yes. Yeah, of course. By the way, Thursday is going to be off, so we'll have no lecture on Thursday. So this homework is going to be for next Tuesday. Okay. Please try your best. Okay. See you next Tuesday.
Okay.
Then. Bye.
Thank you, doctor.
Thank you, Doctor.
Bye.
Bye.